So the third topic that we are going to focus on for Unit 1.2 is basically going to be spectroscopy. And spectroscopy is an experimental technique that allows us to get information about a substance that it is very, very specific to that substance. It's almost like a fingerprint. So what we do in terms of spectroscopy is we utilize something called the photoelectric effect. And we talked about the photoelectric effect last year in honors chemistry, but basically what happens is that scientists over time noticed that if you added enough energy to a metal, the metal would eject an electron. That electron would leave the actual metal itself, and then when it would come back down, it would release light. So one of the ways that we saw that we were able to observe this was when we took metal and we put it into a fire, and it heated up enough and the metal tended to glow. So what happens is that after the electrons are emitted, there's this definite amount of energy that is present. So over to the right here is a diagram or a picture of how we use the photoelectric effect now compared to years ago. Basically what happens is that we have a positive electrode, we have a negative electrode, we fire up a battery, and we crank the current up to get enough energy in there. What ends up happening is that the metal atoms in a vacuum, electrons are ejected because there's some incoming light that comes into this apparatus, and as a result of that, the electron is ejected. It's then detected, and we are able to have an idea as to how much current or energy was put into the system to make this happen. Okay, so the more photons at same energy, the more electrons come off at the same speed. So there's a relationship between the number or the amount of energy being put into the metal and the number or amount of electrons that are being ejected from the metal. So what I really need you to remember, especially for the homework for this evening, is that essentially that one photon equals one ejected electron. So if the other thing that we have to remember is that all metals have a very, very specific amount of energy that is required for an electron to be emitted. So say, I don't know, something like 75 joules of energy was required to emit an electron. If we applied 50 joules of energy, no electrons would be emitted. So if we had 74 joules of energy, no electrons would be emitted. But if we had 75 exactly, we could emit one electron. If we then pumped it up to, say, 100 joules, we can still emit electrons, but it's going to be at a rate that's a little bit greater based on the more energy that's been added. So that's really important to understand about the photoelectric effect. What the photoelectric effect gives us is it gives us the line spectrum that we can identify very specifically for each element. So the first element that this was observed with and documented with through experimentation was hydrogen. So the hydrogen emission spectrum, which is this guy right here, has very specific lines on it, and in between those lines is no color at all. So when we take electric energy and we pass it through hydrogen gas, the electrons in the hydrogen gas are excited and they jump up in energy level and they fall back down in energy level. And what's been noticed is that over time and experimental research, there are always the same 5 line spectrums that we observe when the energy is dropped, when the electrons drop and lose their energy. It's the one right here, the one right here, the one right here, the one right there, and this one right here is often difficult to see. But it's always the same. They always fall between 400 nanometers and 700 nanometers. And they're always the same no matter what sample of hydrogen that we take. So the line spectrum for hydrogen is oftentimes like a fingerprint for hydrogen. And when we get line spectrums for other elements, we can get them for other gases, we can get them for metals. They are very, very specific. That's one of the ways that we are able to gather what elements are involved in stars in space is based on the electromagnetic radiation that's being emitted from those stars. So we can get these spectra from stars and identify what elements are present. So Niels Bohr tried to explain the photoelectric effect and the line spectrum, and what he basically said is that electrons exist. Well, basically what he said was that an atom was like a hotel, and each hotel had very specific floors. And so what would happen is that if we had an electron on, say, the first floor, and in a specific amount of energy or photons were put into the system, the electron would jump up an energy level or two. Well, once it's up at an energy level or two, what would end up happening is that over time it would have to give energy back off and go back to its original ground state. And when it gives back its original ground state, we then see visible light. So that would go back to the line spectrum that we just talked about for hydrogen, the 5 different lines. So the thing of it is that with Bohr, and his idea was that he couldn't necessarily explain why these electrons existed in the very specific energy levels that they did, and why they could go up certain energy levels or hotel floors and then back down to their original energy level. He just basically said, this is what happens, and this is how he tried to explain it. So this picture here is an effort on Bohr to try to describe how that works. So hydrogen has one valence electron, but it has one electron in general. So every hydrogen atom has the ability to have its one electron go from the first energy level, all the way out to, say, the 4th or the 5th, and then drop back down. But as it happens, the electron itself gets excited and comes down, excited and comes back down, excited and comes back down, and it's based on the amount of energy it's put in. So even if we have the current on an electrical system running through a gas tube set at the very same all the way through, the electron is going to absorb energy differently. And when the electron absorbs energy differently, it'll jump up, say, 1 level and then come back down, or it'll jump, say, 3 levels and come back down, it'll jump, say, 5 levels and come back down. And when it does that, it has the ability to give off very specific light waves that you can see. So Bohr explained this through this very complicated calculation, which basically says the inverse of the wavelength is equal to the Rydberg constant times the inverse of the energy level squared that the electron starts with minus the inverse of the energy level squared that it ends with. And so this super complicated formula actually doesn't look that complicated, but in the scope of this class, we don't have to do anything with this formula. We just have to pretty much understand that the difference between the initial energy level and the final energy level, essentially, is equal to the wavelength that we can calculate. So we can use this formula to get us to understand a little bit more about what's happening with the hydrogen atom and its electrons. The problem with this, and we'll talk about this a little bit more tomorrow, is that this formula only works for the hydrogen atom, and Bohr's model of the hotel only works for the hydrogen atom. So as far as we're concerned, that's really important that it works, and it's really important information. But because it only works for the hydrogen atom, there's something else at play. We'll talk about that, like I said, a little bit more tomorrow. Now, here I have 3 different atoms. I've got the hydrogen atom, I've got mercury, and I've got strontium. Okay, so if you look at the visible light spectrum, the visible light spectrum starts with that purple or violet color at 400 nanometers and goes all the way up to 750 nanometers with your reds. So hydrogen has a value or has a line somewhere around 420 and somewhere around 440, somewhere around 540 or 86 rather, and somewhere around 650. Okay, whereas mercury has one right around 410 and like say I don't know, maybe 440, and then it's got something around 590 or 545, and then a bunch of them are around 575. So it has significantly more. And strontium also has a bunch of spectra, but they're all over the place. But what I'm trying to get at with this particular picture here is the fact that every spectrum that we collect is always different, whether the element starts as a gas or it starts as a metal. In order for us to observe this, though, we generally have to heat it up and make it gaseous. So atoms with more electrons tend to have a more detailed spectra. Another test that we can do or perform would be doing something we did last year in Honors Chem, which was a flame test. And the color that's given off when we burn a metal is very, very specific. So for example, copper always gives off the color that's sort of this bluish green. Strontium gives off more of a deep red. So we can compare all of these colors all the time. So like when you're watching the fireworks, what ends up happening is that the fireworks are giving off colors based on the metals that are present. So if you see a yellowish colored firework, chances are we're talking about sodium. If you see a blue-greenish colored firework, chances are there's copper in the firework. If you see a reddish colored firework, chances are we're talking about strontium. So these flame tests are another way for us to get spectrum data that we can go ahead and identify very specific elements from. And you may remember a lab that we did in Honors Chem where we burned some salts that were made of metals, and you had to identify the different type of salt the different type of metal in the salt based on the color. And that is something that actually chemists have been doing for hundreds of years to get very specific data about elements that are present in unknown substances. Okay, so problem set number 2 is based on questions 632 and 634. I know what you're thinking. You're thinking, oh, that isn't so bad. But what it really is it's like A, B, C, D, and A, B, C, D, E. So it is a bunch of questions, but it's still based on the energy equation and the equation for speed of light is equal to wavelength times frequency. So practicing some more of those skills. So good luck with that homework. I will post this video, and then I will also post the answer key to tonight's homework on Google Classroom.